Okay, everyone clicked in? You guys all agree? Most of us agree. We're at 90-some% are saying C, which means that if we have an increase in volume, that is going to correlate to a decrease in pressure. So I agree with you guys, and let's take this one step further. And I want to have you guys discuss, what is it that actually drives that? Our breathing. So I want you to talk in your group. Think about it first for a second. Think if you can define a very articulate way of saying, why does air actually leave or go into our lungs? I want you to be able to define that on a molecular level.
If it's a closed system, you have a fixed space.
Fixed number of particles.
Okay, I thought of it as a closed system is a steel box. It's closed. You can't change the volume. But you're adding more stuff to it. Would that increase the pressure?
So in that case, yes, but the lungs are not. So the question asks... It's like a balloon that you start small and make bigger, that now those particles have more room to move around. What is the L thing? Can't see L going on here.
Like physically is the diaphragm, but the pressure is less than atmospheric pressure inside the lungs, so the pressure can like localize.
Okay. So let's bring it back together, and I want Kira to share her thoughts. Chase. Kira, can you share?
The pressure inside the lungs is less than atmospheric pressure, so the pressure is trying to equalize.
Okay, so this is a really important point. Most people say, well, because there's higher pressure, that means that we're going to go in this direction or that direction. It's all about the relative pressure. So any physical equilibrium like this, if you have an ice cube in water, what's going to happen over time? It's going to melt, they're going to end up at the same temperature. Same thing with physical equilibrium like this. So if you have two bodies of air that are very different pressures, the gas molecules are colliding much quicker on one side, they're much more compact. And on the other side you don't, where's the gas going to go? It's going to go towards higher or towards lower pressure? It's going to equilibrate. So that means the high pressure is going to give up gas molecules and move quickly into the area with low pressure, and then those two are always going to equilibrate. And it doesn't matter which side is our lungs, that's completely irrelevant. Our lungs don't want anything. Those two physical conditions are going to stabilize. They're going to stabilize by going to a place where they're the most similar. So for any gases, that's the case. We're going to use that today to talk specifically about atmospheric pressure and wind that we get into. So this is one way to look at it. There's a diagram. What do you guys notice about the difference in pressure when we're breathing? Between inside and outside?
Not much.
What's the difference?
3. Yeah.
6 and 3 what? Millimeters of mercury, which is also called torr. So 1 atmosphere is 760 millimeters of mercury, or 760 torr. Turns out that the difference between what's in our lungs and what's outside our lungs is ridiculously small. There's only a difference of 760 to 753, or 757, sorry, or 763. There's a difference of 3 millimeters of mercury pressure, pressure. And that is enough. If you put your finger in front of your mouth, breathe in and out a couple times. You guys feel the molecules going by? Too cool to do it? And if you breathe a little bit harder, if you're ever running, and you actually put your hand in front of your finger, you can feel how much force there is from those molecules passing by your finger. That force is generated by having that small of a difference in pressures on two different sides of a particular spot. And we put our fingers in the middle. It's like riptides. So I grew up in Seattle. We have the San Juan Islands. And do you guys know how tides work? Like why you die in tides? Why you can? So maybe, I haven't died yet, but a lot of people do. So you have Washington State, which is awesome. Looks something like this, okay? And there's all these islands that are here. So what I do is I go kayaking when I'm out there. And so I go kayaking around these islands, but it's really, really, really dangerous to go kayaking out there certain times of the day. And it's because when it's low tide, what happens to the height of water in here? Okay, so low tide, there's very little water in here, right? And then as the moon starts to come over this area, and gravity pulls from the moon, pulls water back in here, all that water starts rushing in. And so in the little areas where there's space between the islands, that water rushes to get by it because there's low water over here, right? So that water is going to come in and fill up. To fill all this, all that water has to pass through these little channels between the islands.
Is diffusion a reasonable answer for this?
So diffusion just is like a random movement of things. So I would say diffusion from an area of high pressure to an area of low pressure, or high density to low density. We'll talk about that in a little bit.
Okay.
So I've gone kayaking, and I've been out here in a time when it's changing from high to low tide, and right in that middle time, right between high and low tide, that water's moving so fast through there that you don't go where you want. You go where the water goes. That's it. So I was out there between high tide and low tide, I think. So the water was doing the opposite. All that water was flowing out of here. And there was a pack of hungry seals in front of me, and I was trying to go that way, and it didn't work out so well. So I ended up going right through this like pod of 30 seals, and they were up barking, and it was crazy. Yeah, it was awesome. So that's the same thing with the air in our lungs, right? Let's do this. Click in. What percentage of the volume of our lungs do you think is exchanged in every breath? What percentage of the volume that we have in our lungs do you think is exchanged every time we breathe one breath? Dr. Pierce. All right, a couple more seconds. Click in your answer. What percentage of the air in our lungs do you think we exchange with every breath? Everyone got their answer clicked in?
Is that based off of sea level?
Doesn't matter. It's a percentage. Might be more or less molecules. Closing out?
No.
Closed. 50, 30, 10, 15, 60, 70. Carol, what did you find? So I think the percentage is around 15% of the air in our lungs. I think it's in that ballpark. And Ms. Terrell will correct us when she finds an accurate answer. Is that kind of crazy? Why is that crazy? Yeah, you would think if we were efficient, all the air in our lungs would exchange every time. We'd have access to all that new oxygen we'd pull in. So when you hyperventilate, have you guys ever done that? Get a little dizzy. So we do that a lot, then we actually will change 15%, 15%, 15%, 15%. We actually change a lot more of the air in our lungs, so we have a higher percent of oxygen, which makes us go dizzy.
It's actually 16%, and I know that because when you give someone CPR, you're only giving them 16% of oxygen that you're using when you get it up, because that's all you can breathe out.
Okay, and the air that we're breathing out already has less oxygen in it. So, yeah, more carbon dioxide, less oxygen. Okay, so it's a relatively small fraction. So keep that in mind. When you guys are talking about ventilation in bio class in a couple of weeks, this is going to be really important to think about the diffusion of gas, oxygen from gas into our blood, and how that affects everything else in your circulatory system. All right. So in our class today, I'm going to be focusing on having you guys be able to keep developing your ability to explain gases with molecular terminology. We're also going to use that to talk about, well, how temperature, we've already talked about pressure and amount of gas kind of play a role, but we're going to talk about temperature today as well. How that allows us to make this description on a molecular level. 15. So I think Don and us are right on about the same point, same mark. Okay, so then we're going to talk about extrapolating. We've talked about how our lungs work. We've talked about how those awesome fish are so cool. Hope you guys were here before class and you got to see those fish floating around and those, what are they called, swimmers? Air swimmers. Awesome. Now we're going to be talking about weather patterns. Okay, so this is where we're going today. So this is kind of what we've been envisioning. I've been trying to get you guys to picture these molecules moving around, and that if you move your hand, you can feel any hairs in the back of your hand will feel the molecules moving out of the way. And so envisioning those molecules being there and predicting how they're going to act in different situations is what we're building up. And so this is called kinetic molecular theory, is thinking about a collection of molecules and how they're moving, what speed they're going at, what properties they have. So we have a couple rules for ideal gases. So here are some assumptions that we make with ideal gases. So we're assuming in a gas that all the molecules are continuously moving, there's random motion, and here's the kicker, is that when they bump into each other, they're not like pool balls that lose energy when they bump into each other, that the collisions are elastic. What do I mean by elastic collisions, Demetrius? What does elastic mean to you? Stretching, and what happens when we release something that we stretch that's elastic? Comes back to exactly what it was. So we don't lose any energy. That's the idea of an elastic collision. So on a molecular level, we make that assumption. Do the laws of physics allow that? No, so it's false, right? But we make that assumption for ideal gases. The second thing that we assume is that all of the volume of each gas, the actual space that that molecule takes up, is negligible. Is that true? Do molecules take up any space? Yeah, we know that that's true, right? Because if you have it in a liquid, there's a volume that they occupy. There's a density of those. But when we talk about ideal gases, we're basically saying that they're pinpoints, and that when they collide with each other, those two pinpoints will bounce off each other with an elastic collision. And then the last assumption that we make with ideal gases is that they don't have any intermolecular forces. Once they become a gas, that they just act all the same. We have helium running into water, running into ethanol gas. If they're all gases, we assume that there's no attraction between them. Is that true? No, but maybe they're going fast enough where that attraction is so minimal where we don't really notice it on a large scale. Okay, so these are all assumptions, and that's why we call it the ideal gas law, because it's not reality, it's an ideal scenario. Once you start dealing with gases that are packed in together, high pressure, these start to fall apart. Talk to your neighbor for a second. Why is it that when we pack gases really close together at high pressures, that these start to not be true anymore? Okay, Katie, can you share your thoughts? Why is this not so true anymore at high pressure? You didn't talk about it? Okay, so if you don't hear a question, always ask me to repeat it. Or else you're going to put on the spot like this, and it's going to be kind of silly. Natalie.
You didn't really have an answer, but I was just thinking that it wouldn't be true because the pressure would increase, so then they would just, I don't really know how to explain it.
Dana, you want to help out? Kristen? So many what?
There's like so many collisions because of the high pressure.
Okay, so I like it. So you're going high pressure means that they're either closer together or they're just running into each other more frequently, or really both. So then which one of these starts to fall apart at high pressure? And why? Volunteers. Don?
The elastic one.
Why the elastic one?
Because it's not going to be able to it's going to be transferring too much too quickly. It's going to be transferred.
Okay, so I might twist that a little bit and say, well, maybe each time it loses a really small percentage, but if it hits so many times, small percentages add up. Shane?
The last one they tracked in our presentations, because everyone knows the more pressure you have, like on water, air turns to water. Like it turns to
When does gaseous water turn into liquid water?
extreme pressure.
Okay, so if we compress it, so we could go back to our phase diagrams and look at our phase diagram and see under higher pressure, we might be able to force that to go from a gas to liquid. We can. Where else do we have liquid, so gaseous H2O turning into liquid H2O? What's that?
Close to water.
Close to water, yeah, sometimes I can go in. Brianna?
Is it like if you're like boiling something and the steam's coming off and then it hits something that's a lot colder than it, it'll make like
Okay, so when it cools down, when we have water vapor and it cools down, that water vapor becomes a liquid again. Where else does that happen? In clouds, right? So we have all these water molecules that are gases that are moving around. We start slowing them down or bringing them close together, either one, so higher pressure or lower temperature. When they get close enough together, they form droplets. Those attractive forces come together. So these rules don't really work when you put molecules too close together or you slow them down too much, and then we start to have phase changes and we have other crazy behaviors that go on. And then we have bad things happen where alarms go off.
Sorry.
All right, so take a look at this figure here. And maybe, let's do this first. Before you guys answer this question, let's talk about what it's even showing. Let's ask a question. If you have a sample of gas at room temperature, let's say it's a pure gas. Let's say we have only nitrogen. We have nitrogen at room temperature and we have a balloon of it. Is the speed of that gas all the same? Or do we have different speeds of that gas in the same sample? At a very specific temperature, if we controlled it, only 25 degrees Celsius, is all the gas moving exactly the same speed, or are they moving at different temperatures? Talk to your group, see what you guys agree on. Which one of those two sounds more accurate? Were you able to repeat it? Or?
The temperature is constant. Are all of the particles of one ideal gas moving at the same rate, or are they moving at different rates? The temperature is constant. Yeah. I want to say they're really the same rate, but I feel like it's tricky. Like I feel like you're trying to trick us. So like the logical answer is not right.
Okay, so Sarah, can you share your logical answer with us? So all of the gas molecules go at the same speed. Is that the most logical answer?
No, I don't think so.
So if we have one temperature, we would say that they're all at this speed. If we looked at another temperature that maybe was warmer, we'd have this speed. If we looked at a colder temperature, we have all of them at this speed. That was a terrible line. What's that?
I thought you were asking, say, if you have a gas and nitrogen, are all those molecules in that one sample moving at the same speed?
Yep, that's what I'm asking.
Yeah, but then if they were at a different temperature, they'd be going at a different speed.
Yep, so I'm saying that the first answer that Sarah gave, this is the most intuitive one, is that if we're at this temperature, this is the speed of the molecules, all of them. Right? And that's what this graph shows, and then saying, well, if we had different temperatures, then that is the only thing that would affect and have different molecules at different speed. Does anyone disagree with this? Cosmo?
Well, like myself and Don, we were talking about how when it like depend on how the container is shaped and like where they are in the container, because like if it's closer to the wall, it would exert more pressure, and then they would move faster in that case because they're bumping over.
They're bumping over. Okay, Sarah, you want to add to it? Then you want to add to that description, Don?
I would just say that I think that the graph is an average, because if I'm an N2 molecule and I bump into him, I'm going to lose a fraction of my energy, but then immediately someone else is going to bump into me and I'm going to get it back. So they're all slightly, very, very, very ever so slightly different at the same time.
Okay, so there's some differences, you think, just due to the fact that things are colliding. Kristen?
I had a question. Is speed and kinetic energy the same thing?
Yeah, so we're going to use them interchangeably for gas molecules. We're going to say at a higher temperature, higher speed, lower temperature, lower speed, and kinetic energy is speed, right? Chase?
You said that we were assuming that no energy was lost with the particles and gas hitting each other, but does that hold the same for if it hits the side of the container?
So that's the theory with ideal gases, yeah, is that it would.
So that even with that, they're saying if it hit the side of the container, it wouldn't lose that either? Okay.
Right.
Just wanted to make sure.
I would think that they would all be the same speed, because if they weren't, then isn't that also what like depends on the phases? Because what if some are slower, then that would mean that some might be within the liquid stage instead of gas. So wouldn't they all be around the same value?
So this is what gases look like at a given temperature. So I have on the y-axis how many of them are at that speed, and on the x-axis I have how fast they're going, or kinetic energy is another way to say it. Think about when you're playing pool. Does anyone play pool? Everyone play pool? When you hit the cue ball and you put so much energy into the system, do all the balls move the same speed?
No.
But can you say that if I put more energy in, there'd be more motion that happens? So that's the principle you need to be thinking about, is that although the total energy of the system is something, it doesn't mean that everything is moving at exactly the same speed. It means that overall you could say, well, what's the average speed? If we have this many particles and we have this much energy, then the average speed is this. But we always have a distribution. Some molecules are going very slow, some are bumping into each other and going extremely quickly. So what would this graph look like? So we have an average speed, right? What would this graph look like if we warmed up the sample? Talk to your group for a second. What would it look like if we warmed the sample up?
Is that right?
I don't know. Try.
Make the peak higher. Yeah, I think like it would be higher because like the average would be higher.
What did you do?
Well, I didn't mean for
What was
that
the
to
focus?
happen. The average would be higher, so the peak would be higher.
So the average percentage? So keep in mind, this is how many of them are at that speed. So what you're saying is there's more molecules.
Oh, no.
So I disagree with that.
So, okay.
So the speed is this axis.
Okay, so that's like really, really bad, but yeah.
Okay, so we have Natalie's drawing up here. Natalie, can you explain what you drew?
The bottom of the y-axis is the amount of molecules. So like only is increasing, not the amount.
Right, so we didn't change the number of molecules. What we changed is how much total speed they have, how much kinetic energy is available for them to use. And so what we see is a shift, and you could focus on two things. You could either focus on maybe the average, right? Average is actually probably a little bit left of that, but overall, that the average moves to a higher speed. Does that mean that everything is going at that certain speed, though? So there's a really nice PhET simulation. If you guys want to go play around with this to get a visual of it, Google PhET. And then chemistry. There's a really nice visual that actually shows gas molecules, and it shows them colliding with each other, and what happens when you close the space down that they're in, or you increase the volume, you change the temperature, you add more molecules, all those things. And you can see the results, and you can see the individual particles changing. What would it look like if we cooled the sample down from the original sample? We would have more frequently have gas particles that moved slower. In each of these samples, we still have some, and all of these probably, we have some that are almost standing still. If you think about a game of pool, you can hit the ball incredibly hard, and you still have some balls that are standing still, and other ones that are going really quickly. And that average is we're talking about that the temperature is going to be different. So based off of that now, I think we can go ahead and answer these questions. So which one of these samples represents a sample of nitrogen that is coldest?
All three of those samples have different number of molecules.
No, they have the same.
Okay, almost done.
Number.
Yes, I don't know why it's been doing that recently, but it's been freezing. Closing out. So Alex, which one and why?
I put A because the coldest is going to be like the slowest.
I think almost everybody in the class agreed with you. So we can look at this graph and we can say that the total number of particles in each one of these three graphs is the same, which would kind of be like the area under the curve. The same number of particles are there. But the slower that it gets, the colder it is. So each one of these is a colder and colder sample. But each of them still has a distribution of molecules that are moving at different speeds. And here's the really cool thing about kinetics. We're going to be starting getting into kinetics, right? This is related to kinetic molecular theory. In order for a reaction to occur, going back to Kristen's point, they must have a minimum amount of kinetic energy. Let's say that the amount of kinetic energy they have is correlated exactly with the speed of this. Anything with a greater speed than that or a greater kinetic energy than that can react. Which of these samples has more molecules that can react? Why C? So beyond this line, the only one that even shows a visible amount of molecules that have enough energy, kinetic energy, to undergo this reaction are the ones that are in C, which are warmer. So you guys probably all have heard that the faster you want a reaction to go, the warmer you get it, right? Warmer reactions go faster. This is why. That in order for two molecules to collide with each other, for a chemical reaction to occur, for bonds to break, they have to have so much energy. And so the warmer we make a sample, the more likely that is to occur. So we'll be talking a lot about that using this diagram next week. And that's called the activation energy. All right, so let's go ahead and answer the next question then. You can work in your group on this if you want. Ow.
I would say that
Cool. Make sure you've had your discussion, you click in with your choices.
CO2 has a molecular weight of 35.
CL2 does?
CO2 has 70.
Couple more seconds. Megan, what are your thoughts? Okay, so let's combine. I'm going to keep going back to what Kristen said. So they all have, at the same temperature, right? They all have the same kinetic energy. Each sample has the same amount of energy. Here, I'm going to give you all the same amount of energy. So which ones are going to move faster? Based on your logic, Megan. Yep. The lighter one. If you have a certain amount of energy and you push a little marble versus you push a boulder, which one is going to move faster? The one that has a lot less mass. And so these distributions don't just apply to one sample at different temperatures, but also different samples at the same temperature. So we can look at all of these and we can say which one of the molecules represents the curve C. That one's moving, has more molecules moving faster. So that's going to be the lightest of all of these, which is helium. Can you guys use logic to get through that one on your own? What questions do you guys have on this so far? Don?
The question I might just be, I'm not remembering the back history for it. If what we just said is true, and that is what I picked, but how come if you drop a marble and a bowling ball from the same height at the same time, they land at the same time?
They land at the same time, you said? So if you drop a feather, a marble, and a bowling ball all at the same time, they don't land at the same. If you drop them at the same time, they don't land at the same time. And the reason is because of air resistance, right? Yeah, and marble maybe depends on how far it's dropping, right? So if you take away all of the gas molecules in a complete vacuum, then they all have gravity pulls them all at the same rate. But that doesn't talk about how fast gas particles are moving, because that's more about kinetic energy than about gravity. So those are two a little bit different concepts. Yep, fair enough. Any other questions, comments? Yeah.
So I'm like still kind of confused. So if they're all the same temperature, they're all gonna have the same kinetic energies.
Yep.
But with different speeds.
Yep. Doesn't sound like you're confused.
No, but then you also said that speed and kinetic energy are the same thing. So that's why I'm confused.
Well, so the kinetic energy, okay. So you're right. So I was a little bit overstating the same thing. So by saying speed, speed is speed and mass together, that's force. And so force relates to kinetic energy. So if you have so much energy you put in, that's so much force and equivalent. And so that's mass times acceleration relates back to velocity. So this sample here would have the same kinetic energy as this sample, but those samples all have different mass, so the overall speed is going to be different of those. What about the density? Is the density of all these samples, if we have the same volume, what's the density going to be like of all three of these samples? So if we have the same volume of each at the same temperature, then we're going to have the same number of molecules, but these ones weigh a lot less than these. There is an equation for this. Do you guys want to use this equation? The root means, okay, so say it. Fantastic. That's it. That's all you need to know right there, what Shane just said. Everyone hear that? Dan, did you hear it? One more time. That's it. That the root mean square speed, this thing on the left here, is inversely proportional to the molar mass. That the heavier something is, the faster it'll go. Yes, you can calculate exactly what that relationship is. I don't give a shit. I just want you guys to be able to say that the heavier something is, the slower it'll move if you give it the same amount of energy. All right. So now let's go back to the image that is awesome for some of us. So this image, Mia. Can I zoom in? So I love this image because it really shows the flow, the movement of gases around our planet. So we're going to have you guys explaining some of these by the end of class today. Okay, so go ahead and talk to your group. Click in your answer to this question here. Has anybody here been to the beach? You guys ever go to the beach? Does anyone not like the beach? Yeah, I'm not a fan. Alright, I still go down there, but yeah, I don't like the salt, the heat. Put me in the mountains, I'm happy. Alright, let's go ahead and read the question. It's on your handout as well. Stop reading this question, make sure you guys are on the same page. A couple more seconds.
Yeah, we talked about that in biology.
Yeah.
Were you talking about biology? We actually talked about that in biology. In Dr. Chapman's class? What part of it?
Things are finally being integrated.
It was when we were talking about biomes, and then she was talking about the sea breeze.
Okay, so we're going to get into that in molecular level today. All right, guys. Everyone in? At the beach, we can think of air over the water in relation to air over the land. Which air is less dense in the middle of the afternoon? We don't know. All right, so let's talk about some logic. Let's try to use some logic. The majority is always right? Let's follow that taller peak. I think that's so funny when I see that. Okay, so how do we answer this question? Justin.
Well, when I was thinking about it, I was just comparing solid, liquid, and gases. So
True, but we're talking about the air over two different places, the air over land and the air over the water.
Oh, no, I was thinking like, okay, the difference between gas and solid is going to be.
So we're comparing, maybe I need to draw an image just to make sure we're all on the same page. We're talking about when we're at the beach and we have sand and then we have water. And we have air all over everything. And we're saying what is more dense? And why? Val?
This is just my thought process. So I think that humid air is less dense than regular air, and the water that would be in the air would be over water. There's evaporation going on, so it's more humid, so it would be less dense. More dense. Maybe that's what I meant.
What?
Does it have to do with the water evaporating? Is that going to affect the density?
It plays some role, so I think you guys have a homework problem that talks about what is more dense, humid air or non-humid air. Colleen?
Well, I was thinking that it would have to do with the temperature, and because water stays, if it stays at a more stable temperature than land, it'll still be cooler over the water than it will be over land. So that
Okay. Does everyone agree with Pauline's statement, first of all, there? Does everyone agree that in the middle of the summer, that the air over the water is cooler than the air over the land? Seem reasonable? Land heats up way quicker than water, so that means that the temperature over the water actually stays pretty constant day and night. Over the course of a summer, the water warms up, but not day to night. Okay, so then where do you go with that?
because it's cooler over the water, it would be less dense over the land.
So we have,
Cooler, it's more dense, is what I'm saying.
when the sun hits the sand, it irradiates infrared radiation, which we feel as heat, which warms up this area. Chase?
So when the warm air will rise.
Hold on, we're not getting there yet. So does everyone agree that this air is warmer than this air?
Yeah.
Okay, so then the question is, what about density of them? What's more dense, cold air or warm air? Cold air is more dense if we don't have a container that is confined to. At the beach, is there a container that confines the air over the beach? No. Okay, so this air warms up, and what happens to it? Those particles spread out. These ones are cold, and they stay pretty compact. Hold on a second, Taylor. So, the one that is less dense in the middle of the afternoon is the one that is over the land. Everybody okay with that? All right, so then let's see if you guys can all get on the page for the next question. Which of those two bodies of air is more likely to rise? Saying if you have those two bodies of air next to each other, one of them might rise. Which one would go up? Click in your answer. A couple more seconds. What's that? So, Jose, which one and why?
I said over land.
Why?
Because we just said that warm air is going to rise.
Not necessarily. So warm air, as it warms up, expands. I didn't say it rises.
Well, it's less.
Okay.
Have to rise
Okay, so here's the key, right? We talked about before. It's about the pressure difference, or the density difference in this case. So if you have two bodies of air next to each other, one is more dense than the other, then one of them is going to go up, and the other one is going to go in underneath it. So I agree that the air over the land is going to go up. So then if that's the case, think about the two bodies of air next to each other. And I think you guys talked about this in bio this morning. What does that mean? What direction is the wind going to blow if you're standing at the beach in the middle of the day? I'm glad I'm not hungry when I come to class.
I live in a beach town, and the wind changes direction, so I'm kind of like,
So we can bring that up. All right, closing out. So, Hannah, did you agree with the majority and why?
No, we thought it went from like that way. Like from the land over.
Why?
Because it's warm.
So, I think you're maybe a step ahead of where we are right now. So, that should be across the way. Yeah.
They just said no.
Okay, so you're thinking on a higher level. We'll come back to that in a second. So if we have these two bodies of air, this is more dense, which means that there's more particles packed closer together. It would be really loud in this room if it was for us, so we're not leaving. Set your bag down, Cosme, we're fine.
Nothing in this room is on fire.
Not yet. So that means that this one is going to go up. It rises. When that happens, the cold air comes in and underneath it and fills that space. In a minute, we'll get to what you're pointing at, Hannah. So I agree with the majority here. So let's take a look at what this actually means, what this actually looks like. And here, Hannah's point kind of comes into play a little bit. And Kira, this might play into what you're saying, maybe not. So I want you guys to look at this image, and I want you to look at a few things. Look at the arrows, look at how the arrows are changing, look at where the sun is, the temperature over each. So see how it has the temperature over land and over the ocean at different times of the day? So I'm going to hit play on this thing. One more time. So what point in the day is there no breeze that comes from this phenomenon? Is there no breeze at nighttime? Is there? Is it actually sunset and sunrise?
It says 6 p.m. around there.
Right. Okay, so it looks like right at sunset, and then what about sunrise? Okay, so there's a number of different weather patterns around. Okay. Just Daryl. There's a number of different things going on, and we're not saying that it's just the simplest possible version of this. So Kira, what have you experienced?
I live at the beach, so they're like at 2 different days of one or the other. You can have the wind going out at noon, and the next day the wind is coming in at noon. So it's just.
Is it usually like cloudy or like different things going on, or is it literally the same sunny whatever?
Same sunny.
What beach do you live at?
I'm from New Jersey, so.
That's why New Jersey doesn't fall into the logic.
That's fair enough.
Sorry. So there are many. Maybe we'll state this. Maybe in the big picture, that there's. What's the way to do this? I want to know how many of you guys have been at the beach, standing at the shore in the middle of the summer, and felt the breeze come in. Is that raise your hand if that's a normal thing for you guys. Raise your hand if you think it goes both ways, from your experience.
Yeah, but it's also in the same day. The days are not.
Okay, great point. So if there's a bay on the other side, then the same phenomenon happens on both sides. But typically the air will come in and go straight up. So from my experience of being on sandy beaches, this actually helps explain the majority of the wind currents, but there's also a lot of other things at play. So I'll leave it there. You guys should be able to logically describe these phenomenon, even if you don't experience them all the time, from this kind of a thing. Also, when you look at weather maps, you guys ever watch like the news with the weather on it? They always show like high pressure, low pressure. I'd rather say high density and low density. To me, that makes more sense. That the molecules are packed closer together. The one that's higher density is going to come in contact with low density, and that's going to push one up, and the other's going to go down. When that happens, you have shearing of air, and you get crazy wind. You get really gusty wind going on that's back and forth, because you have bodies of air that are going up and down, and that's when you get thunderstorms and stuff. So this is the kind of image that, if there's no bay, and we have simple systems, then this kind of logic makes sense. So what happens to that air that's hot, that goes up, Hannah? If this air goes up, and this air comes in, where does this air go? Why does it go this way?
Because we're going to have lower pressure, so we're going to have to the high pressure go to low pressure.
Okay, so high pressure goes to low pressure, and we just created a vacuum out here. And that this moved in, so now there's missing air over here, if you will. That when this air moves forward, it leaves behind an area of lower pressure. That pulls this out, and it sucks it back down. So typically, we actually have a cycle where the air goes around like this. Where do clouds usually form in relation to beaches? I'm probably going to get in trouble here because you guys have experienced maybe some different things as well. Where do clouds form? So,
Air warms and comes from the warm air over the land, and then it goes over the water, it cools down and makes clouds.
okay, so where is the most humid air? Out of all these positions here, where's the most humid air? You say 7?
Most humid.
Yeah. Why is 7 the most humid? Because the water evaporates, so we have a mixture, and this air has a lot of water vapor built into it. But this air gets moved over here when this air goes up, right? So this gets moved over, and then it gets heated up. What happens to that moist air when it gets warmed up? It goes up. And then when that air goes up, what happens to the temperature? Cools down, non-ideal conditions, and we get clouds forming as it moves back out in this direction. So a lot of times you will see this phenomenon, not always, that there are exceptions to these rules. Okay? Can you guys rationalize your way through weather patterns based on gas laws? We could do this all in PV equals nRT and have you guys do calculations all day long, but I think I'd rather have you look at the world outside and be like, oh, I can predict what's going to happen when you warm up a gas. It's going to expand. When you expand it, it's going to go up, like an air balloon. And then that might go somewhere else based on other things that are happening. So these are the kind of steps I want you guys to be able to think through and use logic to get through. Any questions? I should say, what questions do you guys have? Any questions? Okay, so last couple of things on gas laws. We've already been using this, so I think Don asked about this the other day, and Val maybe as well. Dalton's law of partial pressures. It basically says that the partial pressure, or how much pressure comes from each individual gas, we measure the total, we don't measure the partial pressures. But if I know that 30% of our air is a particular gas, let's say 20%. 20% is oxygen. I can tell you what the partial pressure of oxygen is. If I go up to the top of Mount Everest, maybe the partial pressure is the same, but the total is different. So that means, or the fraction is the same. So that means we're going to have a lot less gas molecules. So Dalton's law of partial pressure basically says that if we have multiple containers that have gases, we could actually measure the pressure in these two different containers. And if we take those molecules and we put them again into the same container that's all there, then the total pressure is going to be additive of those two individual pressures. So this is usually what they focus on a lot in Gen Chem, and I think it's really boring. But I think you guys can figure out how to use it to do other things. So let's do a couple of calculations along these lines. I want you to be able to figure out the molar mass of a gas based on this information here. sum of all the individual partial pressures, that's what the total is.
Okay.
The answer is not A, whoever just clicked in A. Two of you, no. Try to work on this in your groups. If you get stuck, raise your hand.
The arithmetic is there, not messing up.
All right, I'll give you guys about 20 or 30 more seconds. What's an easier way?
Oh, is there an edge? I just put M
No, it's not molarity.
or MS.
Put A and U.
I can just type the letters A and U.
Yeah, if you're comfortable saying that those are equal to each other, but it's AMU per molecule. This is molar mass, so molar mass shouldn't be AMU.
I'll just pretend to still be asleep with that.
I always
Be
think
creative.
about just like not going down, but I was like, what if the one time I do that?
Can I get a raise of hands from anyone who actually used units in their calculations? Okay, maybe I can just give you a little insight since not everyone's taken an exam in our class yet. I really want to see you guys using units. I'm going to give you the gas constant with a ton of different units tomorrow. And if you guys don't show your units, you're going to get significant points off. Just because that means that whoever's grading your exam is going to have a really hard time following what you did in order to make sure that you did everything that's on there and did it appropriately and used the right things for the right reasons. So please use units because the gas constant in particular is very specific to Kelvin and what type of pressure you're using. So can someone tell me how we would go about taking all this information and trying to figure out what molar mass of this gas was? Salma, you want to share your thought process? Okay, so why would you want to find the number of moles? So the units of molar mass are how many grams in comparison to how many moles of that substance. Do we already have one of those two? How many grams do we have? 4.65 grams. So if we knew the number of moles, then we would already have the molar mass. Okay? So then how did you use PV equals nRT to find that? So 1.00 ATM times 2.10 liters divided by 0.08206 liter atmosphere per mole Kelvin times temperature. What did you have for your temperature? Oops. 300 and what? Okay. And then if you do that calculation, what did you find? Not yet. 0.080521. Okay, that's good enough for now. That many moles. And then what did you do with that? Did anyone do something different? Thomas, do you have a comment? So let's go back and look at our units to make sure we followed everything through. So we have atmospheres canceling with atmospheres, liters canceling with liters, Kelvin canceling with Kelvin. The only thing that is not canceled out is 1 over moles, which brings it back to moles. So that's exactly why we want to put all the units there, to make sure that we might have forgotten something. Okay, so if we do that ratio and we calculate 4.65 grams per 0.0805219 moles, Pat, what did you find for your molar mass?
54.6
grams per mole. And what's another way to say that? If you want it to be in biospeak, you could call those Daltons. Okay, typically for small molecules like this, we're not going to use Daltons. How many sig figs should we have? 3 sig figs. So let's see what you guys had as a class overall. 0.5. I like it. We had a few people write Daltons. We had... Who didn't round the whole time? What did you have as your final answer? 54.5112. So it should be 54.5 grams per mole and not 55.6. If you rounded an answer and then used that for the next calculation, you would have been off by a little bit in your final answer. And I think that all this is worked out, so I'll post these slides afterwards in case you had any questions on that. That's terrible. I don't know why that N didn't actually get plugged in my... This is why I always like working through things instead of having animations for the calculations. Questions? So I hope that what you see is that over and over and over again, what we're trying to do is use these mathematical relationships in order to solve for something that we don't know. whether that be molar mass or the mass of a compound or how much of it we have or all these different things. Shane, you have a question? Grams per, oh, that's the final answer. Yeah, sorry. There we go, is that better? Yeah, so it probably was using 0.0821. So this is why, like I said, I don't like using slides that other people have made in the past for animations. I'd rather do the calculations with us and go with what you guys do is more accurate. You guys are better than my slides. Taylor?
I found an equation that gives you molar mass from the density, and could you always find the density if you have the liters and grams?
Okay, so if you go from density to molar mass, I imagine you're making some assumptions. Did you use temperature in that equation at all?
Yeah, it's density times the gas constant.
Whoa, so hold on a second, let me clear this out. Let me write it out. So what is it?
Density is, well, dRT over P.
Equals?
Molar mass.
Okay, so what is density?
The density would be the 4.65 grams over the 2.10 liters, which you have to convert to milliliters. And I got, never mind. It was way too big. Because like when I got the answer at the end, I got 54,505 altogether, and it kind of is almost like.
So I think that the density that you used, I'm going to guess units killed you on that. So that would absolutely work. That just combines the two steps that we did. So if you go back to the calculations that we just did, then what we basically did is 2.10 liters, that we're plugging these relationships back into here. So we're basically taking the number of moles and we're dividing, well, you can write these out and they'll be exactly equal to each other. So I can't see it exactly in my head right now. But if you use liters here, keep in mind what your gas constant is. Your gas constant has what unit for volume? Liter. Yep. Yep. So that was your only problem. So yeah, that combines the two steps into one. But you'll only use those kinds of equations if you understand where they came from and how they work. So don't just be like, oh, there's this cool, sweet equation I can plug in and use. All right, just a little caution there. See you, Don. All right, one more. Think about another way to engineer it.
Yeah, this right here. That's what I did here.
So I used these numbers, because I didn't divide, then I divided here, I divided these numbers, so I divided this by itself. Oh my God, Grace is tonight. Oh my God, you just reminded me of it. I know, I just forgot.
All right, another 1 minute to at least write down your process. Hey, Val. All right, so how do we go about this? How do we take all this information now? These problems, we're trying to just throw a lot of information at you and see how you use the equations you have to solve a question. So how do we use all this information to solve this question, Kirk? What are we doing? Kirk?
Sorry, my clicker's not working, so.
Don't worry about it.
I started the same equation that we did in the previous problem and finding or solving for n.
Okay, so we have the mass, we have the volume, we have the pressure, and we have the temperature. So you can solve for the number of moles.
Yeah.
So how many moles did you find?
Do you want a rounded number or?
Give me a handful of sig figs. Digits.
I got 0.2501.
Okay. And then what?
Well, then to find the molecular weight, I divided the 14 grams of the hydrocarbon that we have by the number of moles and got 55.968 grams per mole.
You got what? 50?
55.968.
Okay. Is that match up with one of these? Which one does it get closest to? Shane, what did you find? Is that what you did?
I did that, but I also found the empirical formula, so then I divided that by the weight of the empirical formula, and then multiplied it by that.
So the thing is that all of these have the same empirical formula.
No. Well, if you divide,
Right.
if you divide what you get by the empirical formula, it comes out with the constant, like it's 3.988, and then you multiply that by the empirical formula.
Okay. So we could have done this a couple of different ways. We could have found the molar mass and back it in. We could have found this. We could have also used, did anyone do this, where you actually used the number of moles of carbon and hydrogen in this sample? Something like that? So we're right at the end of class time now. So I just want to say that a problem like this, you could solve about 4 different ways. You could say, well, I know that I have 14 grams, 85.7% of that mass is carbon, so I can find exactly how many grams of carbon I have. You can also find how many grams of hydrogen. If you know the grams of hydrogen and carbon, you can find the empirical formula. Unfortunately, that doesn't help you too much for this problem because of that ratio. But using the number of moles, we could go about solving that. So what my plan is for, by the way, we actually got to the end of slides because I had fewer slides than I thought we'd get to. We're having 2 office hours Q&A sessions, one tomorrow 9 to 10, the other 1 to 2. I think I'll do both over here in ICE 314. If anyone can't make either of those and has some questions, I'm happy to stay after class for 15, 20 minutes. So feel free to hang out. Otherwise, I will see you either tomorrow or, what's that? Our exam is here in this room. So come here tomorrow for our exam. 5 o'clock was when we start. Be here a few minutes early to fill out your Scantron form.
We have workshop at 1:25.
No, I'll be in the tutoring center. And you guys will have yours across the hall. So no, it's not the same space. Yep.
Dr. Billy, how much of this stuff today is going to be on the exam?